All right. Welcome, everyone. My name is Jeremy Wallace. I'm the Solutions Architect here at Amazon Web Services. And I'm very excited today to introduce a company who provides millions of time series metrics per second to customers all around the world. And so here to discuss how they've used EBS to lower costs while improving performance and availability of Cassandra on AWS, it's my pleasure to introduce Mike Hefner from Data Engineering at Librato and Peter Norton, who's the operations lead here at Librato. So I'll pass it on to them. And
Well, thanks. Welcome. So just a little background for those who might not know Librato. We are part of the SolarWinds Monitoring Cloud. That is a combination of products you see here. We're both with Librato today, and specifically Librato is a metrics and monitoring solution provided as a service in the cloud. We're consuming, like Jeremy mentioned, hundreds of thousands, millions of time series every second. We store that for you, do data processing on that, provide real-time dashboards, and push all of that data through our powerful alerting platform. We have hundreds of integrations, so based on what you're running in your stack today, there's a high chance that you're already running with something that we support today. And we also have third-party contributions and other integrations that will get you going and get data into the system. Because we are at an AWS conference, I want to mention we also have native CloudWatch support. So you just give us your IAM credentials, we'll pull that data into the system natively into your account. Real-time dashboards, so these work as well if you're firefighting on your laptop, or you want to take this, put it on the wall, and see a real-time updating view of your infrastructure. And all that data that we are collecting, all of that goes through our alerting framework. So everything that you can put on a chart, you can create an alert. And we'll send those notifications out to this popular services that you're using today, Slack, OpsGenie, PagerDuty, etc. So, like I mentioned, we consume a large number of time series metrics, hundreds of thousands every second into the service. We have chosen, and we've been on for many years now, Apache Cassandra as the sort of data store for all of that processing. And Apache Cassandra, one of the major use cases for that is time series metrics. It works great for sort of that scalable high write load. And the ability to sort of horizontally scale that out. All of our data is committed directly into that, and we serve all of our read queries from that as our primary data store for metrics. So we do run multiple Cassandra rings on our infrastructure, and we've sort of split them into, I would say, two distinct categories. We have our real-time Cassandra rings and these are consuming the traffic coming directly into our API. This is the real-time 1-second resolution data. We're storing that for, on about average of about a week retention, sort of that window where you want that firefighting, high resolution, high granularity data. And the challenge is that because that workload is so heavy, we're expanding those rings simply to consume that write load. So a lot of CPU scaling of those rings, much larger ring sizes in general to support that workload. On the other side, we take that data, we downsample that to 15-minute samples, to hourly samples, and we store that for longer, just to give you that sort of historical trend analysis. In those rings that we push that data into, the write load's much smaller because we are downsampling. But the challenge there is that because we are storing that data for longer, we actually use more of the disks on those nodes. So much higher disk volumes on those rings, but smaller rings in general there. So sort of where we were last year, we were running Cassandra 2.0.11 as our primary release across all of our rings, some patches on top of that. We were using the i2 2x large instance type. If you've read the DataStax post or the Netflix post, that's sort of the preferred instance type. Gives you the best balance of SSD performance with larger CPU and memory core counts there. So sort of the default go-to for Cassandra workloads. We had, I think at last count, about 160 of those running total across both our real-time rings and our longer retention rings. Librato has been a long-time Amazon customer, so we were in that camp that we never used EBS. Hearing the horror stories of past, nothing in our infrastructure, Cassandra, or anything else actually ran on EBS at this point in time. So that meant that these nodes were limited to so that 1.5 terabyte you can get from an i2 2x large if you RAID 0 over those drives. So some of the challenges from that, because we were locked in at the i2 2x large, we didn't have flexibility in terms of capacity, in terms of being able to run on larger CPU core counts for those real-time rings where we actually had that high workload coming in. So we ended up actually running these rings pretty hot, well past sort of our even a general comfort level that you should be running Cassandra at. Like I said, because we were not on EBS, that persistent data was tied to that instance. So, when we lost instances, which, we lost a lot of instances over time, it meant that we were spending hours to days just streaming data back into these rings to replace those nodes. And you never want to run at like a degraded ring state for that long of a time. And because we were then limited at that 1.5 terabytes, we had to actually scale those rings out on the longer retention side simply to add disk capacity. We didn't need any more core count. Performance was great. It's simply we were running out of disk space. So sort of just to illustrate, when you're running a ring at a 60, 75% CPU level, and you actually hit the point where you actually do need to scale that up, if you know Apache Cassandra, you know that when you bring a new node in, it starts the bootstrapping process. The existing nodes split up their tokens, stream their data into these new nodes. But they're doing this while they're consuming the existing write load you're pushing into this ring. So they're now doing this double duty to support streaming into the new node, but also handling that existing write load. So you get to this scenario where you then actually have nodes that then end up just collapsing. They just cannot do this much workload starting at that high base CPU level. So we ended up having to do a lot of scenarios where we would try some hacks to get a node, a ring to scale up. Or we just stand up an entirely new ring of a larger size, move data over. But what this generally meant is that we were spending a lot of money on the Cassandra part of our infrastructure. Specifically, at last count, it was approximately 60% of our total AWS infrastructure costs, coming just directly from these i2 2x larges. So that brings us up to sort of late last year. One of the things we had recently, earlier in the year, scaled up our ops team. And sort of one of the major directives that we had for the team was we needed to move off of EC2 Classic and onto the Amazon VPC environment. It was clear from all the new services and new instance types that the future was on the VPC environment. And the team took this as an opportunity to sort of redo all the infrastructure work that we had put in place there. Really go to sort of all the best of breed tools, so SaltStack, Terraform, Flask. And also we wanted to use this then as an opportunity to overhaul all of the Cassandra work that we've done. Go to the latest releases, move to newer hardware. And I think one of the things that really kicked this off was last year at this conference, we attended the CrowdStrike talk on how they had moved their Cassandra workload to Amazon EBS. Saw this talk, really, they were able to do this successfully, got some big wins on that. So that was really sort of the spark that ignited this. If you haven't seen that talk, highly recommend going to see that talk, going back, watching that. I would say large portions of this talk sort of build on that. specifically actually when we started off, our sort of initial spec that we wanted to hit came from a lot of the things that CrowdStrike found. For us, we wanted to go to Cassandra 2.2, latest release in that line. Not too comfortable going to Cassandra 3.0 at the time because we had been successful on Cassandra 2, so we wanted to just go to the latest sort of release in that sort of feature line. Move to the C4 instances, get that additional CPU capacity. The GP2, obviously, we wanted to go to sort of split configuration, data and commit log, and separate partitions. And then just the best of sort of breed OS and system tunings for Cassandra. The big one here for us was also the enhanced networking driver because we were moving to the VPC environment. So with that in place, we started right around about February of this year on this path. And one of the things, we had done some level of performance tuning and stress testing, but what we've found in the past is that we get really the best sort of test capability running our own production workload into a Cassandra ring and actually seeing how that performs over time as you're doing additional compactions and just other periodic behavior of the Cassandra rings. So one of the things we've done early in our process, we've moved all of our Cassandra read and write paths through a single tier in our backend service. So any portion of our site that needs to access Cassandra measurements will actually go through this service to get that data. So the nice thing about that is that we can, with a flip of a configuration switch, is if we stand up a new ring that we want to test a new configuration on, put that configuration flag in place and push our entire production workload into this new ring. This doesn't impact the downstream clients, and we're seeing sort of exactly what that mirrored workload looks like going into that new ring. And similarly on the read side, tad different in that we only pull data from a single ring at a time, but we can actually on a per user basis do a similar process in that we actually flip a configuration switch that pulls data from our new test ring. We can check for correctness, performance characteristics, etc. Obviously dog food that for our own user first, scale that up to maybe some friendlies onto some larger accounts. If anything doesn't work right, just quickly go back and test there again. So with this in place, we sort of started this process off, started our dual writing, pushing our entire production workload into a new test ring that we had set up. And pretty quickly we noticed this behavior that while the rings themselves were performing quite well in terms of CPU volumes were low, EBS metrics looked all right, we were still seeing these timeouts where individual writes would just be completely lost after 10 seconds, where the sort of P99 for us was under 200 milliseconds. And it was just, periodic individual writes that would just get lost in the system. This write timeout, our write timeout in our Cassandra config matched this value of 10 seconds. So something was just getting lost in the system, but spent a lot of time sort of figuring out what had happened here. The downside is we sort of introduced a whole set of variables to sort of the equation here. We had upgraded Cassandra, we'd gone to new instance types, we'd switched to EBS. So we sort of did a lot of back and forth trying to eliminate some of those variables. But the one thing we kept coming back to was when we took the Cassandra workload and went back to our original hardware configuration, we still found that we were seeing these timeouts on the version we'd been using. So continued a little bit more, went to the latest release in the 2.0 line that we had been on before, and didn't actually see those. So at this point, we were fairly confident that whatever was going on was something to do with the Cassandra versions. And like I mentioned, we had been doing a lot of work with our tooling, so we could actually stand up and tear down these rings pretty quickly. So we sort of did this process. So we just went along and bisected the releases between these 2 points of time till we ended up with, to the point where we ended up where between 2.14 and 2.15, we were actually noticing this bug come in the timeouts would appear in 215, and as we backed down to 214, they would drop off. And we sort of second-guessed sort of a lot of our configuration at the time, but it was pretty clear as we went back and forth that when we went down to 214, performance returned to exactly where we would expect it to be. So with that in place, and understanding that something in 215 had broken this, we continued that process, git bisecting sort of the merge commits into that 215 release. Finally came down to a single merge commit that introduced these timeouts. We went through sort of line by line, did a couple PR reviews on that until we found a sort of suspicious time conversion there that didn't use the right factors for converting times on the timeout values for metrics. So patched that, filed this JIRA. We're able to sort of move on from that point to sort of this next level. One of the things we did find when we were actually going through this process is that because we had introduced so many new variables, one of the biggest being EBS, we spent a lot of time sort of second guessing the performance that we're getting with EBS. And there were sort of two major factors that came in here. If the GP2 volumes were bursting, we weren't aware as to if that was actually depleting that balance. It was sort of a mystery quota that we weren't sure if we were depleting that, somehow blocking then on the GP2 device, because those metrics just didn't exist for the GP2 devices. Similarly, the resolution on EBS CloudWatch metrics, 5-minute currently, we ended up installing our own agent, setting a interval of 10 seconds on that, and actually getting the EBS write data from the instances themselves at a 10-second resolution, just to ensure that, because we were seeing 10-second timeouts, that there wasn't something hidden in those 5-minute averages that potentially we were hitting and causing that blocking. So I would recommend that as well if you are running on an EBS workload that you might potentially want sort of a higher resolution metric there, pull those from the instance themselves. On the second point here, earlier last month that was actually released. So the GP2 burst balance metric is now available. So if you're going on to this, if you're testing EBS, you should be able to see that and see if you are depleting that burst balance for your devices. So that next sort of struggle that we hit as we were standing up and tearing down these rings, not always tearing them down as we wanted. We didn't actually shut down Cassandra cleanly, which meant that when we actually would stand it back up, it would have to replay a large portion of the commit log. And we actually hit bottlenecks on the 200 gigabyte GP2 volume that we had assigned for that. We had the 600 IOPS that you get max for that. You were able to burst over that. But we would actually see as these long 15, 30, even longer startup times from that. And it was pretty clear that the commit log for us was sort of a bottleneck. We wanted to sort of continue testing. We had moved to a 1 terabyte volume, obviously additional cost there. We'd also tried just putting it onto the data disk, not what we would like. We'd prefer to have separated those. But that sort of kept us going in this sort of general testing process. And one of the things, it just sort of happened that, around the same time, this Twitter conversation between Jeff and Eric was ongoing. And Eric had mentioned that they had a lot of success with the new throughput optimized EBS volumes, specifically for the commit log volumes, and that they were obviously cheaper performance-wise for the same amount of storage. So as we were still in our sort of early days of this configuration, we actually gave this a shot right out of the gate, and it worked well for us. We were actually able to set up, move it from a 200 gigabyte GP2 volume to a 600 gigabyte ST1 partition, and get that additional capacity, get those additional IOPS. However, still be able to not completely sort of blow out the cost there, because the ST1 is just a little under 50% of the GP2 costs there. And for us, kept that commit log separate from the data. And so that brought us up to our last sort of struggle that we hit on this journey, which was as we started to scale up our read load, we started to see what was in the logs as small message drops across our Cassandra rings. It would start slow, maybe over a few hours, but over the period of a day or two, it would actually grow to essentially encompass the entire ring. All the nodes were timing out, dropping messages in between them, even though the rings themselves were completely fine in terms of capacity. CPU was low, network volumes were low, even the EBS performance was fine. So we were able to roll the rings periodically, which would sort of fix things for a day, but it would then slowly start creeping back up again, which was obviously not okay for us. I think this was now like 4 to 5 months into our testing framework, into our testing sort of period. The cost for this was growing. You know, we've been running a lot of dual hardware. Some of our RIs were starting to expire on I2s. So it got to the point we were sort of stuck here. We needed to really sort of reach out for additional help, see if we can sort of get past this stage in our testing framework. So wanted to give, we actually called up the Last Pickle. So they're a Cassandra consulting firm. They're a really great team. If you haven't worked with them, they were very understanding of sort of where we're at in our position, the sort of urgency to move forward. So we got on the phone with them, did a sort of quick walkthrough of the code. They actually took some of the messages in the logs, were able to identify where sort of that, where those drops were coming from. And it turned out that it was in something called the network coalescing module that had been added to Cassandra previously. And what that does is it combines small packets sent over the wire into larger packets, typically to sort of reduce network overhead, particularly very high packet volumes. So we turn this off. There is a ability just to disable this entirely. So they suggested we actually try this out across our rings. We turned this on, and yeah, after about 2 weeks, we hadn't seen any of these additional timeouts. So great, you know, we had sort of solved all the remaining problems for us. Obviously, downside of turning off network coalescing is that you are spending more on the network throughput. But for us, we weren't at a volume yet that we were seeing any real change in the performance, you know, of our read and our write volumes. So for now, you know, it was now July. We had actually then finally gotten our first production ring up, shut down the old I2 rings that we'd been running there, and, you know, just decided that, hey, we'll live with that sort of network overhead for now. You know, it's a future item to sort of come back and take a look at. So flash forward to today, so where we are actually sitting now. We have sort of our 2 ring types, the real-time ring configuration and a longer retention rings. Not a lot of major differences. We do use the C4 4X larges on our real-time rings where we need that additional CPU capacity for that heavy workload. And then on the longer retention rings, you know, the CPU workload is not as great, but we do want somewhat additional memory capacity, so we have been using the M4 class machines there. And obviously the longer retention rings, we've doubled the amount of disk storage that we can run there with. So I think one of the biggest improvements we saw, we went from running at 60 to 75% CPU volumes down to less than 25% CPU across most of our real-time rings. This essentially equated, and also other, you know, Cassandra performance improvements, equated to almost half a second latency drop in our P99 right side. So significantly better performance right side, read side as well. This was, you know, a much better improvement from where we were before. From a cost perspective, this is actually, if you looked at our real-time ring configuration, we were at about 120 nodes that were running across our real-time rings. We dropped that down to just 66 of the C4 4X larges. If you added in the total cost of the additional EBS EBS volumes there, came out to about a 35% savings. But this is, honestly, like I said, we have a lot of additional capacity. We can actually grow into sort of the savings that we have there and hopefully increase sort of that saving factor over time. On the longer retention side, not as much of a savings initially out of the gate, but we now actually have twice the amount of disk capacity there. So once again, we totally expect to grow into these savings and see a lot more value there as well. One thing also, obviously, on the real-time configuration, excited to take a look at what the sort of C5s will do for this cost factor for us. So that's sort of the journey that we took to get to where we are today. And I'm going to hand this over to Peter to sort of talk about the new operational story that we have.
All right. Okay, you can hear me, right? So this is the new world, right? And usually in operations, new means bad or at least scary. And we clearly had a lot of time to get here. But in the while we were doing all of this work, we were thinking about how are we going to make this so that we can make our lives better. And what's interesting is if you've ever, I hope most of you are here because you use Cassandra and you're looking at making your life better. And the hard part is when you're normally doing a recovery or you have a failure, Cassandra's very slow. In the same way that Mike described the scale-up behavior, you have the same issues when you're recovering. The ring is down, it has less capacity, and you have to reflow all your data back in. It's a lot of work, and you can cause a collapse when you thought you were redundant enough. What EBS lets you do, and VPC, getting an ENI and VPC lets you do, is it actually lets you pretend that the node didn't go down. You can reattach those resources to a new node. And we were a little dubious about that, but we talked to some people who had done that, and we found that it works really, really well. Now, it acts like it didn't die. And so we kind of live this CloudOps dream of like, we have no extraordinary application or Cassandra level work to do when we bring a node back up after a failure. And so we are actually reducing our mean time to recovery because we still can't control when a node goes down, but our recovery time is so much better that it doesn't cause as much panic or as much worry during the recovery process. So the other thing we can take advantage of here is that you can see we brought up a lot of rings to experiment with when we were doing the git bisect, when we had those ring timeouts and failures. We kept bringing up software, we kept bringing up different rings, we took them down if something would delay us for a few days, and we'd bring them back up and reconfigure them and try things out over and over. So it's really important to us to be able to do this whenever we need to. The more we can automate it, the faster and easier it is, and the easier it is to store the data without paying for the instance, the better it is. So we help Mike's team out with that often, and we can bring these up on our own if we need to. And it just is much better than having to disrupt an active ring to run an experiment, to be able to bring up a new ring, try something out, and then bring it down, whether it's configuration, disk, instance type, et cetera. It's just become a lot better for us. Now, the way we do this, the tools we use for it is Terraform. And I think of what Terraform does as being the substrate. The substrate is all of the infrastructure that has a lifespan longer than a single instance. So for us, the primary resources we have here are EBS volumes, the ENIs, and the security groups that go along with the new ring. Each one gets its own set of those resources, and that way when we bring these up with Terraform, they endure past any failures, and we don't have to worry about the state machine of a particular system trying to bring up new ones or not by making decisions. They just only do attachments of these existing resources. One of the other things that's nice about that is that when we bring these resources down, because they've all been purpose created for this one particular ring, when we're done with the ring, we know that all the resources can be removed again. I say that because clearly that would be what you would expect, but if anyone here has started doing AWS from scratch, we have a tendency to attach like security groups to multiple things because they seem similar, and after a while you're not sure what the purpose is. And I think of that as cloud hoarding, and this helps us avoid that particular pitfall. You can get over it many ways, but for us this was a really great clean start when we moved to VPC, and I highly recommend this or something like it to make that work out. So I mentioned that Terraform deals with things that last longer than an instance. For all of our instances, we launch rings with SaltStack. SaltStack lets us do a lot of automation around that. It lets us launch an instance. It automates attaching the EBS and ENI because it has all of the things we need to do discovery and configuration to find those resources and bring them together. The Salt API also lets us put guardrails into the process and procedures that are very straightforward. So even though we do a lot of tricky stuff inside of it, we have a really straight path from start to end. We launch things the same way we create rings would be the same way we scale rings. The commands we actually run when we're in the trenches are the same things we did when we stood it up, which is great. Now, how this works out for us, and it looks simple, but what happens for us is that we have an EBS and we have an ENI, and they're durable. They don't die when the instance dies, and that's part of the configuration that we do with Terraform. And so when we actually have an instance failure, right? I mean, sometimes you can control when the instance fails, right? You want to change a node, you suspect maybe it's not performing up to par, you can control it. And you still want to be able to do your shutting down of listeners, you want to be able to do a flush and a drain and a stop to make sure you have a controlled shutdown with your data, but sometimes it just fails. In either case, once you get to that point, instead of having to do recovery, instead of having to do a replace address and wait for this whole thing to go through the very laborious process of recreating that node in the ring, what happens is the instance's termination becomes the initiation for the EBS and the ENI to get disconnected from it. And at that point, you can just replace the instance. And so our salt configuration only works on the attachments. When we launch a new node, these resources get attached. We run our configuration. We tell it, OK, you're ready, rejoin the ring. And it's as though, in about 10 to 15 minutes, it's as though the node had just taken a nap and rejoined the ring. It had never crashed, per se. There's no recovery. It just starts, hints are replayed. We do extend our hint time a little bit to a few hours just in case something goes wrong, but that gives us plenty of room for recovery. And so once it starts, it's back to normal. Now, the other aspect of dealing with issues is that disaster recovery usually means with Cassandra, or the generic way to do it with Cassandra is you do SS table snapshots and then you take those to S3. And the biggest problems there are, one, that's very intensive on the same interface you're using to give customers their data. And so you have the lower bar of data that you have for customers, and then this really high bar with the CPU sending as much data as it can to S3. It's a lot of data, and it's a lot of resources that we would rather not have to interfere with our business. And also, we have a lot of redundant data. The larger the SS tables get, the less likely they are to get compacted out, and the more likely it is you're re-uploading the same data over and over to S3. When it gets to S3, you then have to run a pruning process that will eliminate the redundancy. Even that way, when you do that, you end up with a relatively high S3 bill. With EBS, snapshots make this a lot better. We have our own ops API. That ops API lets us initiate snapshots from cron. It lets us make sure we know they're done. And then it lets us clean them out after a period. And the way EBS snapshots work is that it does block level differences. And so a lot of that manual pruning gets taken care of automatically and in a smarter fashion than what we would be doing manually on S3. Well, not manually, but what we would be doing ourselves. So, wait a minute. All right, there we go. So, yeah, that word right. Sorry. So yeah, so the other thing that we really like, and Mike alluded to this before, is that we've liberated ourselves from having our storage, our memory, and our CPU tied to the instance type. The I2 instances are really performant in some respects, but they don't really, well, you have i3s now, which are great, but they didn't really offer a high ceiling to what we wanted to do. Now what we can do is we can take our storage and we can say, okay, we anticipate there might be something where we need more CPU, and we can roll through and we can change the CPU type, we can change the instance type, and we can say we need more memory, or we need more CPU, or we just need big. And we can do that across an entire ring without having to destroy it, or at our own choice, we can bring up a new ring and flow the data to that and retire the old one. It gives us a lot more flexibility, but we can do it with the same procedure over and over again. We do work that procedure, and that procedure has been, because of that, it's been the same for bringing up the instance, for bringing up an entire ring, for expanding the ring, and we practice it over and over, and that's super important. And after all that, we still have some additional challenges and some interesting insights into how Cassandra has been doing for us, so I'm going to hand this back to Mike.
Yeah, so just wanted to sort of finish up with some sort of thoughts and ongoing stuff we're looking at, specifically sort of how big data systems access disks and how that, particularly on if you are running on EBS, sort of impacts performance there. So taking a look at Cassandra specifically, and I think this pattern holds true for similar other systems. Cassandra has two different disk access modes. The default is the memory map mode. So what happens there is Cassandra will take all of your SS table files, your indices, et cetera, map those into memory, and then as reads access addresses within those files, the operating system will fault those pages in, performing the read query underneath, and does that at a 4K block period at a time. The other mode, which is standard, does the sort of typical boring read-write system calls to access those files. And that's more there for systems where memory map is not available, so particular Windows distributions and other systems. So the memory map system works great, particularly when you're performing these sort of small random access row reads. So if your user query is actually just needs to pull back 3K of data, the 4K read means you're only doing an additional 1K of overhead there. You're not pulling in lots of additional data just to serve that very small access. Similarly, performance tuning guides for Cassandra suggest keeping the read ahead small so that you're not also reading in a lot of additional data in front of what you're doing to do those sort of small performant row reads. Now, the thing that doesn't fit into this pattern is compaction operations. So if you're compacting a 100 gigabyte SS table, essentially you are moving through that file in a sequential pattern from beginning to end. So what we sort of see is if you take a look at a ring, and what we did here is we set up a 3-node ring. This is consuming a portion of our production write traffic, but it's not actually serving any read traffic. So any reads that you're seeing from the EBS volumes are from those compaction operations over time. Reading in SS tables, compacting those down to fewer tables on disk. So if you take a look at the metrics here in the bottom, you can actually see that the read and write throughputs that we're seeing are about the same. They're spiking to about 10 megabytes per second, but it's sort of mirrored between both the read and write side. If you take a look at the write ops in the top left there, we're spiking to about 100 IOPS per second, writing out this data. But if you then take a look at the read IOPS, they're actually spiking to about 20x the write ops. So we're actually having to do about 2,000 IOPS on the read side simply to do these large compaction operations over time. Visualize another way, if you take a look at your average read and write IOPS size, on the right side we're doing averaging about 120K per IOP, whereas on the read side we're only hitting about 4 or 5K. And this maps directly to that 4K block size that we're faulting in individually, page by page. So what does this actually mean? Well, for us, this impacts our costs directly. On many of our rings, we've had to size our EBS disks much larger than the actual storage capacity that we need on them, because we just need to support this sort of base IOP load that you get with the compactions and be able to get that IOP capacity from the higher capacity that you get on GP2 volumes. And this is because the IOP size for GP2 is optimized up to 256K. So if you're operating at a 4K level, you're much lower than that. You're not really efficiently using the GP2 volume for this. What could potentially be done about this? We sort of want to propose this idea of sort of a hybrid disk access mode. So sticking with memory map reads for your row queries, so those small random access reads, continue to do that with memory map. That works well for that. But when Cassandra in this case needs to do a compaction or a scrub operation or any of those sort of large sequential operations over a large file size, is actually then falling back to a standard mode where we're just doing those boring read-write system calls, which would allow us to chunk the read size based on the underlying block size of the file system. Obviously, in this case, for GP2, would be setting that somewhere up to 256K. I'd love to say that we have a PR ready to go and ready to merge into the system. But what we actually did is we took that same 3-node Cassandra ring, and we took one node in that ring and set the read ahead to that 256K. So once again, it's only doing the compaction operations over time. What we actually saw was on the top graph here, you can see the green line, which is our node with the 256K read ahead, is actually only, pretty stable, somewhere under about 500 IOPS per second, whereas the other nodes are continuing to spike all the way up to 2K there. Similarly, the bottom graph there, the blue line is showing the new read IOP size for that new node. A bit more spiky there, but actually hitting all the way up to about 60K or so. So a lot more performant there. If we aren't using a lot of that disk capacity because our data retentions are much shorter, we can actually shrink the size of that GP2 volume and cut the costs that we're allocating to that a lot. So yeah, sort of in closing here, walk through sort of where we started last year with our Cassandra workload on Instance Store. Walked through sort of the journey and the struggles sort of we had moving to EBS with Cassandra. But now that we're there, we sort of showed you really like all the benefits, sort of operationally, big benefits on the operational sort of ease factors. And then sort of finished up on some of the concepts, improvements that could be seen now that we are actually seeing new metrics running on EBS with Cassandra. So I think some takeaways, we find in this test and other sort of performance issues that we've had with Cassandra is make it very easy to test your identical workload on Cassandra as early as possible. Stress tests are great as well, but you really don't see what it will look like until you get that workload onto the rings. I think the best, the nicest thing with EBS is it gives you that instance flexibility. So if you need more CPU or maybe you need more memory for higher heap sizes, you have that flexibility of instances and can move around if needed, actually, even if that initial decision of instance type wasn't correct for you, or they announce C5s and you want to move over to those. The operational side, obviously, completely different story. MTTR is much shorter for us. We're not staying up all night, sort of babysitting a bootstrap operation anymore. And the flexibility or cut the cost for us. We have a lot more headroom to grow into on a lot of these rings, and we'll sort of continue to see the sort of cost improvements for us. And a few things that we want to look into, sort of short-term future. Definitely sort of start kicking the tires on the Cassandra 3.0 stuff. They've done some different work with the SS table modules there, so curious to see how that potentially impacts sort of the disk performance metrics that we see with EBS. And clearly we need to figure out why the network coalescing for us doesn't work as well. Cut down on those EC2 transfer costs a bit. So yeah, I'd like to thank everybody, and you can catch us on the Twitters, or if you're on the showroom floor, stop by the SolarWinds booth.
Or if anyone wants to just come on up and ask us about what's going on, we'll be here for a few more minutes. It might be easier just to come on up and talk if you have questions or whatever.
Thanks.